Good morning, students. So, in the previous class, we discussed about cell and EMF of the cell and potential difference across the cell, or which is nothing but our terminal voltage. So, in this today class, we discussed about combination of the cells, and before going to the combination of the cells, if you know about the Kirchhoff laws, which are the basic laws fundamental for this entire this current electricity topic, you can solve this grouping of the cells easily. So first I will explain about the Kirchhoff laws. Actually, without the Kirchhoff laws also we can find the EMF of the effective EMF, or that means we can discuss about the combination of the cells. And but if you know about this Kirchhoff laws, then it will be easy for you. So first I will explain about this Kirchhoff laws. So as we know Kirchhoff law, we already that means we know one type of one Kirchhoff law in heat transfer. In heat transfer, we already defined it one Kirchhoff law. Now this is a Kirchhoff law in current electricity, right? And so now in this, that means when the circuit is simple, when only one cell and one resistor or two resistors are connected in series, then you can find the current or potential difference just by using the Ohm's law. So if suppose circuit consists of more complicated, like more branches are there and more number of loops are there included in that, that means more number of resistors are there such that more number of loops are there in that circuit, then it is somewhat difficult to apply the Ohm's law for such a circuit. So generally such a circuits we can solve by using this Kirchhoff laws there. So there are two laws in this, so I will explain now. That is the use of the Kirchhoff law. So that means you can find current in any resistance or potential difference across any 2 points, and we can find the effective resistance in the circuit. So that means we can do all the circuit analysis with the help of this Kirchhoff laws there, the help of those two laws. And so now let us see about this first law here. So this first law, Kirchhoff first law. So that Kirchhoff first law is nothing but we also know it as. So let us name this. It is a first law. Now I am defining here. So now this Kirchhoff first law is also called current law or junction law. That means it is also named as Kirchhoff current law. So we call it as KCL. So Kirchhoff current law, or we can also call it as a junction law. So simply this indicates when two or more connecting wires are joining at a point here, right? Suppose say, then that is nothing but we call it as a junction. When two or more wires are joining at a point, then we call that as a junction, right? And so now here some currents are flowing into the junction, and say some currents are flowing out of the junction like this. Suppose I am taking this as I1, I2, I3, and this is I4 and this is I5, right? This is the junction O. That means now here this Kirchhoff's current law or the Kirchhoff first law simply states that we can express it in two ways. Simply the simplest way is the sum of currents flowing into the junction is equal to the sum of currents flowing out of the junction. That is a simple statement of this Kirchhoff law. At any junction, sum of currents flowing into the junction is equal to sum of currents flowing out of the junction, which we already know. And in fluids, we already applied such a concepts there, right? In fluids, we already applied the rate of flow concepts there. Like suppose in fluid, in a pipe is suppose it is dividing like this. So it is AV, the area of cross section is V and velocity of the fluid is V here. And suppose say this is A1 and this is area velocity is V1. And suppose say this velocity is V2 and area of cross section is A2. And so then here that fluid current is nothing but here we name it as the rate of flow of fluid. So that rate of flow of fluid we can write as AV is equal to A1 V1 plus A2 V2, right? So the net rate of flow is nothing but rate of flow flowing through this pipe and through this pipe. So that will be equal to the net rate of flow here. So it is nothing but like now we are writing like I1 plus I2. I is equal to I1 plus I2. So this is nothing but current, fluid current entering the junction, and this is nothing but current leaving the junction. So that we already applied in fluids there, right? And so now the same thing we are saying in terms of electric current here. So then sum of currents flowing into the junction is equal to sum of currents flowing out of the junction. So that means in this, can you say which are the currents flowing into the junction? So first write the statement there. First Kirchhoff first law. So Kirchhoff first law states that sum of currents flowing into the junction, is equal to the sum of currents flowing out of the junction. It is based on, that means Kirchhoff first law. Kirchhoff first law is based on law of conservation of charge. So that is important here. So it is based on law of conservation of charge. So sometimes they will ask about this. First law is based on what? So first law is based on law of conservation of charge. So it based on law of conservation of charge means whatever the charge is flowing to this junction, so the same amount of charge is flowing out of the junction. So no accumulation of charge is taking place at any junction. So that means if 10 coulombs of charge is flowing here, if then 3 coulombs of charge is accumulating and only 7 coulombs of charge is flowing, then charge is not conserved. But it is not happening like this. If 10 coulombs of charge is flowing into the junction, then same 10 coulomb of charge will flow out of the junction. So that is nothing but there is no any accumulation of the charge at any junction. So that we can conclude that it is based on law of conservation of charge. Next, first law is also called junction rule or Kirchhoff current law, KCL. We simply call it as KCL, Kirchhoff current law. For the junction shown in figure, the Kirchhoff first law can be expressed as, so observe here which are the currents flowing into the junction. I1 is flowing here. Draw this diagram and write that equation. I1 is flowing into the junction, I2 is flowing into the junction, and I3 is flowing into the junction. So I1 plus I2 plus I3. So this is the sum of currents flowing into the junction is equals to sum of currents flowing out of the junction. So I4 and I5 are the currents flowing out of the junction, right? And so then that is nothing but simply our simple statement here. So the Kirchhoff first law is very simple. So sum of currents flowing into the junction is equal to sum of currents flowing out of the junction. So I1 plus, in this example, I1 plus I2 plus I3 is equal to I4 plus I5, right? Now actually this can also be expressed in another way. So this can also be expressed in another way means, now suppose if I am writing this equation like this, I1 plus I2 plus I3 minus I4 minus I5 is equal to 0, right? So that means now this can also be written as, simply I can say it as a sigma I is equal to 0. That means this also we can call it as a first law now. So now this is nothing but another way of expressing the first law. That means first law can also be expressed like this. Sigma I is equal to 0. That means now in this statement we can call it as algebraic sum of all the currents at any junction is 0. So but while applying this rule, you need to remember that we need to apply a sign convention. So that sign convention is nothing but current flowing into the junction is taken as positive and currents flowing out of the junction as taken as negative. So that means here in this equation already you can observe that I1, I2, I3, they are the currents flowing into the junction, they are positive, and currents flowing out of the junction, they are negative here. I4 and I5 are negative. So that this total sum will be equal to 0. So mention this. So after writing this equation, write this, and after this sigma I is equal to 0, now write this. Therefore Kirchhoff first law can also be expressed as Kirchhoff first law can also be expressed as the algebraic sum of all the currents at any junction is 0. At any junction is 0. While applying this statement, we should take the currents flowing into the junction as positive. We should take the currents flowing into the junction as positive, and the currents flowing out of the junction are taken as negative. And the currents flowing out of the junction are taken as negative. So that means either you can write like this or you can write like this. This will be the easiest form. So you can remember this: currents flowing into the junction is equal to current flowing out of the junction. So that is about Kirchhoff first law here. So let us see a simple problem based on this first law. Now here, for example, I am taking this circuit here. That means a junction is represented here. Right. So now I am giving some values here. This is some 10 amperes. So now here I am taking this as I, so we need to find this I value here in that circuit. So that means in the circuit shown in figure, that means in the branch of a circuit shown in figure, find the I value. That means here we need to find the I value. That means these are the conducting wires here. That what I am showing here, all these are conducting currents. The current in these different branches are shown here. So this current we need to find. So right. So now here simply I am taking this. I am naming these junctions here. So let us name these junctions here. Suppose this is A, B, and this junction is suppose as C, and this is D. So you can solve it directly. So just I am writing the stepwise here. So that means at junction A. So let us apply at the junction A. And so now here first let us apply at the B, so that you can apply at the junction A then, because at the B direct unknowns will be there. So now I am taking at the junction B, that means this junction. Then there, suppose I am taking this, some current is flowing like this. Some current is flowing like this in this direction. I am taking this as suppose say I1 along the direction, right? And so now let us apply the junction law at that point here. Current flowing into the junction is equal to flowing out of the junction. That is our statement. So then I1 is flowing into the junction, and this I2 is, that means 2 amperes is flowing out of flowing into the junction. So then I can write this as I1 plus 2 is equal to 4 by applying this. Therefore this I1 is equal to 2 amperes you will get. So this is our I1 value, right? And so now similarly let us apply at the junction A here. So at the A, suppose now I am taking this current as some I2, current between AC. And so now I can write this as at junction now let us see here at junction A. So now at junction A, let us write this first law here. So current flowing into the junction is equal to current flowing out of the junction. So 10 amperes is flowing into the junction. I1 and I2 are flowing out of the junction. So that means I can write this as 10 is equal to I1 plus I2. So therefore this 10 is equal to I1 value we already calculated. So 2 plus I2. Therefore this I2 is equal to 8 amperes. So right, so that is the current flowing in that between A and C. So that is 8 amperes. So next let us consider between at the junction C here. So at the junction C if I consider, then you may consider, suppose I am taking this current as some I3, right. So now let us apply the junction law at I3 at the junction C. So at junction C if I apply this first law here, so then we can write this as I2 is equal to I3 plus 1. So at junction C, I2 is current flowing into the junction and this I3 and 1 ampere are flowing out of the junction. So you can write this value as I2 is 8, I3 plus 1. Therefore, I can write this as I3 is equal to 7 amperes. So that is current between C and D. That is a 7 amperes current is flowing there, right? Now finally, now we can apply at the junction D there. So then at the junction D, so finally I am writing here at junction D. So if I apply this Kirchhoff first law at the junction D, so then you can write this as at junction D means, now again observe the currents flowing into the junction. This I3 and the 3 amperes are flowing into the junction and this I is flowing out of the junction. So I can write this as I3 plus 3 is equal to capital I. Therefore, this capital I is equal to I3 value, we can write this as 7 plus 3. So that it is 10 amperes. So that is the 10 amperes is our required current there, right? So this 10 amperes is our required current. So that means no need of doing all this, no need of writing all these steps here. So directly you can do the simple calculations here and you can calculate here itself at the circuit in the diagram itself you can calculate there, right? And suppose here how to decide the direction of current in this direction is, suppose if you don't know the direction of current you can assume in any direction here. If you are getting negative sign for this current, then that indicates that just we need to reverse the direction of current. For example, here we don't know the direction of current. For example, if you are taking in opposite direction, then if you are getting -7, that indicates the current will be flowing opposite of our assumed direction. Then we need to reverse the direction of the current there, right? So it is a simple application of this first law. Now let us take one more example. So let us take a circuit like this, and here so then 10 amperes current is flowing here. So 3 amperes is flowing here and 2 amperes is flowing here, and this is the current we need to find. So current in this branch we need to find here, how much current is flowing here, right? And then here suppose say here 4 amperes current is flowing like this. So it is a given circuit. So then we need to find this I value here. So here also I will write the junction wise how to apply this. You may solve it directly also. So just I will explain the procedure how to solve this by junction wise. So then here I am naming these junctions as, suppose say this is junction A and this is B, and let us take this as some C, and this is the junction D. And so here some current is unknown, here I am taking this as some I1, I1 is the current here, and next suppose here I am taking this current as I2 here, and next I am taking this current as I3. Then this is the capital I is our unknown value there, right? And so now first let us apply at junction A. So at junction A if I apply, so current flowing into the junction is equal to current flowing out. So then this is 10 is current flowing into the junction is equal to 4 plus I1, and therefore I1 is equal to 6 amperes you can write, right? So that is the current flowing in that I1 value here, that means between A and B. And then next, similarly, let us apply for this junction B. So let us identify this current value I2 here at the junction B. So at junction B, currents flowing into the junction is equal to current flowing out of the junction. So that is nothing but I can write this as I1 is equal to I2 plus 3. So therefore this I2 is equal to I1 is nothing but 6. So 6 minus 3, 3 amperes. So therefore this I2 is equal to 3 amperes. So it is a current at the junction B. And next similarly we can apply this at the junction D. Then finally at the junction C we can apply here. So at junction D. So at junction D if I apply, currents flowing into the junction are like 2 and 4. So then it is I3 value is 6. So I3 is 4 plus 2 we can write. So therefore I3 is 6 amperes. Right. So it is a current flowing in that path there between D to C. And finally you can apply at the junction C. So therefore I can write this at junction C. We can write this as I2 plus I3 is equal to I. So then I2 value is 3 and this is 6. So that is equal to I. Therefore I value we can write as 10 amperes, right? So that is a current required value here, required current flowing through that path. And actually you can also say directly, this much lengthy calculation is not required, or no need of writing the steps like this. So then simply you can solve like you can take totally this this rectangle, you can consider it as a one junction, right? And so now directly you can apply the current flowing into the junction is equal to current flowing out of the junction here. And so now here current flowing into the junction is nothing but I can say it as sorry, this is 9. 6 plus 3, 9, sorry. It is 9 amperes. And so now directly we can solve this circuit here. So directly we can solve that circuit as, you can treat this rectangle as a junction, single point you can consider. Then for this 4 wires you can apply like current flowing into the junction is equal to current flowing out of the junction. So then current flowing into the junction means this 10 amperes and 3 amperes. 12 amperes is flowing into the junction. So then here already 3 amperes is flowing out of the junction. The remaining 9 amperes should flow out of the junction. So that current flowing into the junction is equal to current flowing out of the junction. So directly you can solve here. If they are asking like any intermediate part here like I3 or I2 or I1 values, then you can solve like this. That is a simple way of applying this Kirchhoff first law, right? I hope you got some idea about this Kirchhoff first law. It is very easy only, the Kirchhoff first law application. And so now let us go to the second law, Kirchhoff's second law. So this Kirchhoff's second law. So write this Kirchhoff's second law. So in this, first write the statement, the algebraic sum of all the potential changes or in brackets potential drops, potential changes or potential drops in a closed loop is zero. Algebraic sum of all the potential changes in a closed loop is 0. That is sigma v is equal to 0. Sigma v is equal to 0, or more clearly we can write as sigma E EMF plus sigma IR, this is a potential drop across the resistance, plus sigma Q by C is equal to 0. We know already these terms here. This is EMF and IR is the resistance and current, Q is the charge and C is the capacitance here. because we will discuss that later about the capacitance in the next topic. After current electricity, I will explain about this capacitance. So that means in this topic we won't get such a terms here, only you will get such a terms, and instead of this resistance it may be internal resistance or it may be external resistance may be there. So for both of them we will write like IR only, internal resistance or external resistance. So that means third term won't be there in this topic, right? If such a capacitor is also connected, then we need to write that potential difference across the capacitor as QC. So that means what I am saying, this term is not required in this topic. So after completion of capacitors, you will get such a problems also based on this. So that is actually this potential drop meaning here. That means generally three types of elements may be present in a circuit. In general, in our circuits, three types of elements will be present in that circuit. A cell, then potential difference across the cell. That means EMF of the cell. Potential changes means EMF of the cell we need to write. If internal resistance of the cell is there, then across that internal resistance we need to write. If external resistance are there in that, we need to write. So potential changes across that resistance, whether it is internal or external, we write IR. And if capacitor is there, then we write the potential difference across the capacitor as QC. So if you add all these potential changes, then its value in a closed loop value will be 0. So that is nothing but our second law statement here. The algebraic sum of all the potential changes in a closed loop is 0, right? And so next write some points about this second law here. Second law, Kirchhoff's second law is also called loop theorem, because it is generally applicable for the closed loops. Loop theorem or Kirchhoff voltage law. So in shortcut we will write like this, KVL. Kirchhoff voltage law, KVL. Next, it is based on law of conservation of energy. So you need to remember this point here. First law is based on law of conservation of charge, and the second law is based on the law of conservation of energy. That means about the energy we will discuss later in the heating effects of current. There I will define this electrical energy. So then you will get about how it represents this energy there. So there I will explain. Or simply you can observe this, whatever the energy produced at the different elements, it may be resistance or stored in the capacitor. So all those energies are supplied by the cell only. So that if you are adding all those energy changes, then you will get 0. That is simply meaning here in terms of potential difference if I write here. Then in terms of this potential, that means in terms of energy means that is here, the total energy produced in the circuit at the different elements, it may be resistance or capacitor, all those energies are supplied from the cell only, right? So that is nothing but in terms of energy there. So that is, it is based on the law of conservation of energy, and it is also called the KVL. Kirchhoff voltage law. So generally we are now further onwards I will explain, I will write in terms of this KVL, Kirchhoff voltage law, and first law means KCL, Kirchhoff current law. And now here while applying this Kirchhoff second law, we need to follow certain sign conventions there. So those sign conventions are important while you are applying the Kirchhoff law. So then Kirchhoff laws are very easy to apply, but these are the very important in this total current electricity topic. Remember this, for any complicated circuit, we will discuss some techniques later in the circuit analysis while finding the effective resistance. If you are not getting any idea how to apply such a techniques, then the only way is we can apply the Kirchhoff law there to find the either any parameter regarding the circuit, like current in the different branches or potential difference across different points, or when you want to find the effective resistance between the points there, right? So such an importance it will be there for this Kirchhoff law. And as I am saying, these Kirchhoff laws are very easy to apply. And only if you remember this sign convention, then it is clear. So then here, for example, I will take a loop here, and based on that loop, I will explain this simply. So I am taking a simple circuit here. So sign convention I am going to explain now. So then, so while applying the Kirchhoff law, first we need to decide the direction in which you are going to apply the Kirchhoff law. That means in which we are traversing that circuit there. That means in which we are traveling that circuit, along which path we are going to apply. Whether you are applying like this or whether you are applying like this. That is our choice. So here suppose say current is flowing like this. So now you may apply this Kirchhoff law in that particular loop either in clockwise direction or in anti-clockwise direction. That is our choice, right? So first in sign convention, so sign convention. So first mention that while applying Kirchhoff law, we should follow the following sign convention. We should follow the following sign convention. So in that first point, so Kirchhoff law can be applied by traveling the circuit either in clockwise direction or in anti-clockwise direction. Either in clockwise direction or in anti-clockwise direction. That means first we need to follow a particular direction here, that is our choice, right? So either we may follow either clockwise or anti-clockwise direction, that is purely our choice. It doesn't depend on the direction of current. You may follow in the direction of current or opposite the direction of current, there is no difference. So next point. That means now particular elements now I will explain here in detail. So next point let us write here. In case of cell, when you are traveling from positive terminal to negative terminal, then EMF of the cell should be taken as negative. That means for example here if you are traveling from in clockwise direction if you are traveling, then here you will travel from positive terminal to negative terminal. That is the meaning of traveling here. You are applying this Kirchhoff law in clockwise direction. When you are reaching the cell, then we should travel from positive to negative terminal. So when you are traveling positive to negative terminal, here the EMF of the cell we should take it as negative, minus sign we should consider here. If we travel from negative terminal to positive terminal, then EMF of the cell is taken as positive. Next, in case of resistance, when we travel in the direction of current, then potential drop across the resistance is taken as negative, minus IR. Then potential drop across the resistance is taken as negative. Minus IR. But when we travel opposite the direction of current, then potential drop across the resistance is taken as positive, that is plus IR. Potential difference across the cell is taken as positive, that is plus IR. Means it is now same for either internal resistance or external resistance. We follow the same sign convention there, right? And actually the third element capacitor will be there, as it is not complete, it is not required, or just if you want to mention that, you may mention that point there. So in case of capacitor also, actually some points like positive and negative charged plates will be there. So now if you are taking like positive and negative plates, now capacitor is represented like by parallel lines of equal length. So the one is positive and other is negative plates will be there. Plus and this is minus. So its capacitance is C here. So now when you are traveling from positive plate to negative plate, then potential difference is taken as minus Q by C. And if you are traveling like from negative plate to positive plate, then it is taken as plus Q by C, where Q is the charge present on this plate here, positive plate. So about capacitor, nothing to worry, we will discuss later in detail. Q is the charge on this capacitor. So just write the sign convention. In case of capacitor, when we travel from positive plate to negative plate, then potential difference across the capacitor is negative, that is minus Q by C. But when we travel from negative plate to positive plate, then it is taken as positive. That means potential difference. Then potential difference is taken as positive. That is plus Q by C. So that means these are the sign conventions here. So all these points, 3 points we can express as a single point here. So basically the sign convention is when you are traveling from high potential to low potential. When you are traveling from high potential to low potential, potential drop will be there. That means potential is decreasing. So the decrease in potential is represented with the negative sign. Whether it may be resistance or whether it may be cell or whether it may be capacitor. What I am saying, when you are traveling from high potential to low potential. So in case of battery, if I consider here, right? So then here it is high potential. Now when you are traveling from positive potential to positive plate to negative plate means we are traveling from high potential to low potential. That means potential is decreasing. So that decrease we are representing with the negative sign. Similarly, when current is flowing like this, then suppose I am taking this as point A and this is point B here. So which is high potential there? Point A is higher potential because we know current flows from high potential to low potential. So then we are traveling from high potential to low potential. Then it should be represented with the negative sign. That means potential is decreasing. So the decrease in potential is represented with the negative sign. But whereas when you are traveling in opposite direction, like from low potential to high potential, from B to A, now there the potential is increasing. So it is represented with the plus IR. So simply when you are traveling from high potential to low potential, the potential drop is represented with the negative sign. When you are traveling from low potential to high potential, the potential gain is represented with the plus sign there. So it is a simple sign convention. For all these we are expressed in a single point like this. So you may mention that also. So all the above points can be expressed as all the that means you may mention all the above sign convention can be simply expressed as when we travel from high potential to low potential, then potential drop is represented with the negative sign. And when we travel from low potential to high potential, the potential gain is represented with positive sign. The potential gain is represented with positive sign. So actually now while applying this Kirchhoff laws, first we need to assume the current direction here, because they won't give any current directions as I mentioned, whether it is when we are traveling in the direction of positive current or negative direction. In the circuit they won't give any current direction, so we need to assume the current directions there, right? And so then the advantage in Kirchhoff law is you can assume in any direction. The only restriction is it should obey the Kirchhoff first law. If it is obeying the Kirchhoff first law, you can assume the current in any directions there. So that means you may consider from low potential to high potential or high potential to low potential. In any direction you can take as you wish. The only restriction is it should obey the Kirchhoff first law, right? That means junction rule is to be obeyed at any junction. So like that you can assume in any directions there. So now after doing all the calculations, if you are getting a negative sign in for any current, so that indicates that the current what we are assuming is a wrong direction. We should take the current in opposite direction. The numerical value will remain same, right? So the numerical value will remain same. Only we need to reverse the direction of the current there. So that is the only that is the main advantage of this Kirchhoff law here. That means there is no any confusion while applying the Kirchhoff law. You can assume the current in any directions there. So mention that point there. So while applying Kirchhoff laws, first we need to assume current in different branches. First we need to assume the current in different branches of the circuit. Current in different branches of the circuit in any direction such that it should obey the Kirchhoff first law at any junction. It should obey the Kirchhoff first law at any junction. After calculating, if we get the current with the negative sign, that indicates the direction of current, what we assumed is wrong. So simply we should take the current in opposite direction. With the same magnitude. That means magnitude of current will remain same with the same magnitude, right? So this is the important point you need to remember. So from this point you can observe that how simple this Kirchhoff law is, right? That means you can assume in any direction. You can assume the current in any direction. There is no any confusion while applying this Kirchhoff law. Got it? So the only thing is you need to remember those sign conventions there. That means here as a capacitor is not there, only about the cell and resistor you need to remember. I am again explaining. For the cell, when you are traveling from positive to negative, then it is minus EMF we need to take, minus E, and when you are traveling from negative to positive, it is plus E. And for the resistance, when you are traveling from in the direction of current, then it is minus IR, opposite the direction of current means plus IR, right? So now let us take one example here. So then let us take this circuit here, and we need to find the current in different branches there, right? So I will give some numericals also so that you can do some calculations here. And so now here I am taking this, suppose say here EMF of the cell is say 10 volts, and this is the internal resistance here 2 ohms. And so then this is 4 volts and this is 1 ohm. And here this resistance I am taking it as some 12 ohm. So it is the resistance here. So those are the values given. So we need to find the current through the external resistance and current in the different branches of the cell. That means current flowing through each cell. So write that question. In the following circuit, in the following circuit, find current through the each cell, current flowing through the each cell, and a current flowing through the external resistance, and a current flowing through the external resistance, right? So now that is a given circuit. So the first step while applying the Kirchhoff law is like in Gauss law. In Gauss law, first step is we need to assume the Gaussian surface, right? So here the first step is to apply the Kirchhoff law is we should assume the current directions there. So as I said, that is your wish. So then generally let us start the current from the cell with the larger EMF here. So I am starting from here. So this current I am taking as for example I1, right? So that I1 is flowing out of the cell. So that means now when you are reaching this cell, this point, this junction, now you may get the confusion. If you don't know that point, what I said now, whether current is flowing like this into the positive terminal of the battery or current is flowing out of the positive terminal of the battery. Both the possibilities are there, right? Because cell may be in charging state, it may be in discharging state, or it may be in open circuit. All possibilities are there here. So current may be there entering the positive terminal or current may be there leaving the positive terminal. But here the advantage, that means directly you can't say here whether it is flowing out of the cell, flowing into the cell. So but here the advantage of this Kirchhoff law is you can assume in any direction. So here also I am taking that it is flowing out of the cell like this. If our direction, that means if our assumption is wrong, we are assuming I2 is flowing out of the sign, out of the cell. If our assumption is wrong, then you will get the I2 value with the negative sign. If you are getting the negative sign, then simply finally we should reverse the direction of the current. Current is actually flowing into the cell. So that is the final assumption we need to, final conclusion we need to make, right? And so now here this current I am taking as I. So this is a current flowing here, I. Now again at this junction, the current will divide here. So this current will be I2 is flowing here and this I1 will flow like this. And always remember, while taking the current distribution in the different branches of the cell. So whatever the current coming out of the positive terminal of the cell, the same amount of current should enter into the negative terminal of the cell. So now here from the cell, from the positive terminal we are taking I1 is flowing out of the cell and here I2 is flowing out of the cell. So those two are combining here. Here again they should divide. So here you can't take I1 and here you can't take I2 here. What? Because here current I2 is flowing in this direction and then current, same current I2 should flow into the negative terminal of the battery. If it is flowing, I1 is flowing positive terminal of the battery, now the same I1 should enter into the negative terminal of the battery. So current flowing into the positive, into the coming out of the cell and entering into the cell, both always must be same. So otherwise the conservation of charge won't be satisfied there, right? And so that point is a fundamental point. In any complicated circuit, you should take that point there. That means you should consider that point while taking the current distributions. Whatever the current coming out of the positive terminal, same amount of current should enter into the negative terminal also, right? So now that is the current distribution. Now just let us apply the Kirchhoff junction law here. Suppose say this is at one junction I am taking here. So let us name this circuit here. I am taking some names A, B, C, D, and this is E, F, right? And so now let us apply this by KCL at junction B, right? It means Kirchhoff current law at junction B. So at junction B Kirchhoff current law if I write, then what we can write is I1 plus I2 is equal to I. Current flowing into the junction I1 and I2, that should be equal to the current flowing out of the junction, right? And so now this let us take it as equation 1 here. So that is simply our Kirchhoff first law. We are applying the Kirchhoff first law at the junction B. And so now here, as I said, we already considered the current distribution. Next we need to apply the Kirchhoff law. So while applying the Kirchhoff law, as I said, you may apply either in clockwise direction or in anti-clockwise direction. So that is also purely your choice. So in whether you may apply clockwise or anti-clockwise, finally you will get the same answer. So now here, so the direction first time we need to define here. So I am applying this. So I am writing that KVL here by applying by KVL for loop ABEFA, right? That means we need to mention such a loop here that indicates, that automatically indicates we are following in that direction. So ABEFA, that indicates it's a closed loop. We are applying for such a closed loop here, right? And so now let us write this Kirchhoff law here. And so now we need to apply our sign convention by following in that path from A to B. So from A to B, is there any element? Element means like resistance or cell or capacitor. Is there any such a device? So no device is there. That means this is a conducting wire you may consider here, so that there is no potential drop when you are traveling from A to B. Got it? Next, when you are traveling from B to E, when you are traveling along this direction. So now you can observe this. We are here cell is there. So now in that cell we are traveling from B to E. B to E means positive terminal to negative terminal. All of you know that longer line is nothing but positive terminal and shorter line is nothing but negative terminal. So we are traveling from longer line to shorter line. That means positive terminal to negative terminal. Then according to our sign convention, EMF of the cell is negative. So we should write it as -4, right? Next, we are here resistance is there. So now the resistance, we are traveling like this. We are traveling from B to E along this direction, but the current is flowing in opposite direction. So for the resistance, when you are traveling opposite the direction of current, the potential drop across the resistance is taken as positive, opposite the direction of current means. So we should write this as IR. So I is nothing but I2 and R is 1 ohm, right? And next, E to F. So E to F, is there any element? So it's a pure conducting wire, so that there is any potential drop here. So no need to write any term here. Next, when you are traveling from F to A, resistance is there as well as cell is also there. So let us write for the resistance. Now we can observe that in case of resistance, we are traveling from F to A. That means in the direction of current. In the direction of current means it will be negative. Minus I1 into 2. IR formula, minus IR. Next, cell is there. So for the cell, we are traveling from negative terminal to positive terminal. So that means we are traveling from low potential to high potential. Negative terminal to positive terminal means EMF of the cell is positive, we should consider. So it is plus 10. So this value is equal to 0. So those are the potential changes in that loop, in that closed loop. So then our second law is nothing but algebraic sum of all the potential changes should be equal to 0. So now let us write this as one equation here. So I am writing like this. I can write this as I2 minus 2I1 plus 6 is equal to 0, or we can write this as 2I1 minus I2 is equal to 6, right? And so now I am naming this as equation 2. Let us consider this as equation 2 here. And next, so here two unknowns are there here actually. Basically two unknowns are there. And if you are taking this as another unknown, then three unknowns are there. Then the three relations we need to write. Already we have mentioned the two relations here, right? So just one more relation is required here. So for that one more relation, you may take either this loop like A, C, D, E, F, either this outer loop, or you may consider this loop B, C, D, E, B, this loop. That is again your choice, right? You may consider this first cell and the resistance, or you may consider the second cell and the resistance, you may consider. That is also your choice. By taking any loop, you will get the same answer only. Suppose I am taking this. So I am taking this as by KVL for loop. So let us write this A, C, D, F, A, right? And you may write, you may include these letters also if you want. That means A, B, C, D, E, F, A you can write. So as no elements are not writing those points there. So directly I am taking from A to C and D to E, D to F, right? And so now let us write that Kirchhoff law for this loop, the same sign convention. So you yourself write this equation here. And so now from when you are traveling, again we are taking this in this direction here. You may apply in opposite direction also, you will get the same relation. You may check by writing in both the directions there. The final equation you will get the same. So now when you are traveling from A to C, so here no element is there here. This is the junction. Even though point B is there, B is a junction, and so no conducting. That means no electrical element, either resistance or cell is not there either in this part or in this part. And so that means this is a total conducting wave. So A and C will be at the same potential. So that means there is no potential drop. Next, when you are traveling from C to D. Now when you are traveling from C to D, here this potential difference, that means resistance is there. And so that resistance we can write it as when you are traveling from negative in the direction of the current, then potential drop is negative. So I can write this as minus I into 12 IR. So that current we are taking it as I, right? And so next, from D to E, D to F if you consider, again this is a total conducting wire, and so there is no any element, so we can write directly there. Then from F to A if you consider, then here we are traveling in the direction of current here for this resistance, so potential change is negative. So minus I1 into 2. Next, for the cell if you consider, we are traveling from negative terminal to positive terminal. Negative terminal to positive terminal means EMF of the cell is positive. So plus 10 is equal to 0. So then here by using our Kirchhoff junction rule, we know already this I is equal to I1 plus I2. I am directly substituting that value here. Therefore this is I1 plus I2 into 12 minus 2I1 plus 10 is equal to 0, right? So I can write this equation as 14I1 plus 12I2 is equal to 10. Or you can divide with the 2 here, so that this value I can write this as 7I1 plus 6I2 is equal to 5. So let's suppose this is the equation 3. Now simply we need to solve all these equations here. That means equation 1 and equation 3, equation 2 and equation 3 you can solve. So that you will get the I1 and I2 values there, right? That means this here I am substituting from equation 1 instead of I, just I am writing this I1 plus I2. And you can solve these two equations so that you will get this I1 and I2 values here. So just I am writing this from equation 1 and 2 and 3. So just this equation I am multiplying with the 6, and so that we can add with this equation here. So directly I am writing that equation as equation 3 plus 6 into equation 2. That means equation 3 is, I will write here 7I1 plus 6I2 is equal to 5. And now this equation is nothing but we are multiplying this equation with the 6. And so now I can write this as 12I1 minus 6I2 is equal to 36. So now let us add those two equations. Then this term will be cancelled here. So then I can write this as 19I1 is equal to, this is 41. Therefore I1 is 41 by 9 amperes. Right? And so that means we are getting this positive sign, means our I1 direction what we are assuming is right. I1 is 41 by 19 amperes. So what we assumed, our assumed direction is right here, correct here, right? And so now by substituting either in this equation or in this equation, you can calculate our I2 value. So then let us find this I2 value here. Now from equation 2. From equation 2, I2 is equal to, I can write this as 2I1 minus 6. So this is nothing but I2 is equal to 2 into I1 value is 41 by 19 minus 6. Therefore it is 82 minus 19 into 6 by 19. Now we can observe this. Now this 19 into 6. That 19 into 6 is nothing but I can write this as 82 minus 114, right, by 19. And so now we can observe this. Now we are getting this I2 value as negative here. Therefore this 82 minus, that means 114 minus 82 minus 114 means we can write this as 18 minus 32 by 19 amperes, right? So then that is current I2 value here. Then current I2 is nothing but, now we can write this as I2 value we are getting is negative sign here. Now that you can observe here. This I2 value is 32 by 9. So then 32 by minus 32 by 19. So minus 32 by 19 means now we are getting this negative sign here. So that negative sign means, as I said, the direction of current is opposite to our assumed direction here, right? And so that actually current is flowing from flowing into this positive terminal of the cell here. So that is the conclusion of this current here. That means you may mention this conclusion here. Therefore, as I2 is negative, the direction of current is opposite to our assumed direction. And therefore, this I value we can write it as, I will write the I value here from equation 1. Now I is equal to I1 plus I2 we can write. So I is nothing but 41 by 19 I1 value, and this value is minus 32 by 19, right? And so then this is nothing but 9 by 19 amperes. So that is our I value there. So that is I value. Now I values we are getting positive, so our assumed direction is correct only, right? Now in the same question, if I ask like, that means now while writing this I2 value, here I2 value I am substituting along with the sign. According to our assumption I am writing here, or by reversing the direction, after that also you can apply the junction rule, you will get the same. That means once if you reverse the direction of the currents there at the junction B, for example, so this I1 is flowing like this and I2 is now flowing like this. Now I2 means, now if you are taking this direction, then you should take this as positive value, 32 by 19. And I is flowing like this. Then our equation is nothing but I is equal to, that means actually this I1 is equal to I2 plus I value we need to write. So this I is equal to, you can write this as I1 minus I2. Now this I2 value we need to take a negative sign, that means positive value here. This is 41 by 19 minus 32 by 19. Because already we are reversing the direction, you need to take positive value. That means after reversing the direction, you may calculate this I value, or if you are calculating with the same directions, then we need to substitute this I2 value along with the sign in this equation, right? So then in any way you can do here. So that is I1, I2 values there. In the same question, for example, if they ask like, what is the potential difference across this cell, terminals of the cell? So if they ask like that, potential difference across the terminals of the cell, then you need to identify whether the cell is in discharging state or the cell is in charging state, or whether it is open circuit. Now this cell of 10 volts is in which state? Discharging state, because current is flowing out of the positive terminal of the battery. When current is flowing out of the positive terminal of the battery, then it is discharging state. Now here this cell is, we got finally current I2 is entering this like this, current is flowing like this. When I2 is, finally we are concluding I2 is like this here. When I2 is like this, then current is entering the positive terminal of the second cell. When current is entering the positive terminal of the second cell, this cell is in charging state, right? When the cell is in charging state, that will be equal to E plus IR. So that means here for this you will get E minus IR formula we need to apply, and for this E plus IR formula we need to apply there. And so that means in the problem, if they ask the terminal voltage, we need to identify the cells, whether the cells are charging or discharging, we need to write here. So that only we name it, we named it as terminal voltage. So they may ask to find the terminal voltage across the cell, or they may also like ask like find the potential difference between the terminals of the cell. So that means I am writing that value also, potential difference across 10 volts cell, that means first cell, is equal to, for this we need to write E minus IR, that means I1 into R1 you may write. So which is 10 minus that I1 value we already calculated, which is 41 by 19 into R1 is 2. So you can simplify this. So it is 190 minus 82 by 19. So therefore it is 108 by 19 amperes, sorry, volts, voltage, this is terminal voltage. So, right. So similarly you may find the potential difference across the second cell. So first cell is in discharging state, then the second cell is in charging state. How to identify charging or discharging? Just by identifying the current directions there. So then potential difference across 4 volts cell, that means second cell. So that's terminal voltage, we can write this as, let us name this as V1 across the first cell. Now I am naming it as E2. So E plus IR we need to apply here, right, because it is in charging state. So that is the difference between charging and discharging there. So then this is 4 plus. Now here once if we take like this, we need to substitute only magnitude. That magnitude of this current is 32 by 19 into this is 1. So then you can write this as 76 plus 32 by 19. Then V2 value is 108 by 19 volts. So now you can verify this. Now finally what we are getting is potential difference across the first cell and potential difference across the second cell is same. You observe this. So that is the beauty here. Now that means both the cells are in parallel, right? This E1 and E2 are both are in parallel. When the cells are in parallel, their potential difference across them will be same. Whether cells may be in parallel or resistors may be in parallel or capacitors may be in parallel. Whenever that elements are in parallel means potential difference across them must be same. So potential difference across the first cell and potential difference across the second cell is same. You may calculate the potential difference across this resistance also. Definitely will get the same value. 108 by 19 volts only will get, right? So that is, I may simplify this. We calculate already I value, then I into R you may find that. Definitely will get this 108 by 19 because all those 3 are in parallel, we can say that. That is meaning there potential difference will be same across any elements. Whether the cells may be charging, some cells may be charging and some cells may be discharging. But potential difference across them will be same when they are connected in parallel, right? And so that is a way of applying the Kirchhoff law, and that is a way of finding the potential difference EMF of the cells here. So right. So then Kirchhoff law is very easy. So while applying the Kirchhoff law, you need to remember the sign conventions. According to the sign convention, you need to apply that. So then after solving these equations, you will get such equations by taking number of loops. If more number of loops are there, then automatically more unknowns we need to assume there. So when you are assuming the more unknowns, then automatically more equations you will get. As we know, generally the general procedure is if suppose say 3 unknowns are there in that problem, then 3 equations we need to write. If 4 unknowns are there, then 4 equations we need to write, and we need to solve those 4 equations there. So by solving those 4 equations, you can calculate these unknown values, whether it may be currents or potential difference or like potential difference across the cells, we can calculate. And more problems we will solve basing on the Kirchhoff law in the coming classes. But just in the next class, I will explain this effective EMF calculations there. Because by finding the effective EMF, actually I introduced this Kirchhoff law here. So after finding the effective EMF, after discussing the effective EMF, we will solve more problems based on this, right? Most based on this Kirchhoff law. Right, thank you.